Hi, I'm Chiao-An from Purdue University presenting our work, DeepNet with Subsampling Layers Unwittingly Discard Useful Activations at Test Time. This is a joint work with my collaborators, Ziwei and Raymond. Our work is motivated by the following idea. In deep learning, we often assume that data has identical or similar distribution during training and testing time. Therefore, we tend to use the same model with the same procedure for both. On top of this, test time augmentation, or TTA, is a commonly used practice to enhance test time performance by applying additional data transformation. So we ask a simple question. Is there anything else that could be done at test time to enhance the performance? We then observe these behaviors in convolutional neural networks. Most have subsampling layers to reduce the size of the feature map. Pooling operations is one of the most popular choices. However, the pooling layer often selects one possible output while discarding the others. Here, we denote the selected index as S. For example, in the one-dimensional scenario, the default S equals 0 is used, while the other S equals 1 is discarded. In the two-dimensional scenario, S equals 0 is used, and the other S equals 1, 2, 3 are discarded. Based on this observation, we hypothesize that this discarded information is useful. Moreover, this discarded information can be easily retrieved by shifting the input. Or in other words, by changing S and manipulate how the subsampling layers operate. In this work, we show the usefulness of the discarded features. During test time, our method can work under both learning-free and learned settings. Our method works on both classification and segmentation. Our method works on CNNs and VITs. Here is an overview of our approach. Given an input image, our approach manipulates the subsampling layers with different configuration S to output multiple feature maps, and then aggregate them together. Our approach is designed to answer these two important questions. How do we aggregate the retrieved feature maps? How do we know which feature maps should be retained due to the limitation of the computation budget? To aggregate the feature map, we first align the feature map based on the shifting bias caused by the subsampling configuration. Next, we propose an aggregation function for each of the following two settings. Under a learning-free setting where no additional labels are required, we can use entropy function weights for aggregation since the entropy of the logit is correlated to the confidence. Under a learned setting where a small set of additional labels is at hand, we train an additional attention layer to learn the relationship among all features. To retain the best feature maps, we design a greedy search algorithm with a priority queue scored by a criterion function. For example, we start from a default configuration node with all S set to 0. We span this node and get its three neighbors with configuration 100, 200, and 300. Each node is scored by the criterion function. We then expand the node with the lowest score and get its three neighbors 210, 220, and 230. This process is repeated until the budget limit is met. The criterion function can be learning-free, which is based on the entropy function, or learned, which is based on the aforementioned attention matrix. Our approach includes some other extensions. It can be applied to vision transformers. For example, VIT starts with a few convolutional layers with large stride as subsampling operations, while swing uses patch merging operation to reduce token length. The figures show how we can retrieve the discarded features in patch merging using similar techniques. Our approach can also be applied to image segmentation by viewing it as a per-pixel image classification problem. We can compute an entropy map instead of a value for the criterion function. In our experiment, we first compared to traditional learned TTA methods. In TTA, multiple transformations of the same input image are fed into the same network. In our approach, only one image is fed, but multiple subsampling configurations of the same network are used. Since only the subsampling operations are modified and the rest is unchanged, our method is more efficient than TTA. In the first table, we experiment with SOTA learned TTA method under the same budget limit. We observe significant improvement using our approach. In the second table, we report the max and latency with and without ours. We show that not only does our method perform better, but it is faster and requires fewer resources. We also show the performance gain of our model on image segmentation and vision transformers. In these cases, more budget up to a limit can achieve higher accuracy. In summary, we show that using discarded features in the subsampling layers is beneficial. We also demonstrate that our approach works on various testing settings, architectures, and tasks. Our code is available on GitHub, and please refer to our paper for more details. Finally, if you have any questions, we are happy to answer them during our poster session, October 1st, 10:30 poster session 2. Thank you for listening.